Hello everyone, I'm Sesha Vadlamudi, a student pursuing her Masters from the Department of Computer Science from Stevens Institute of Technology. Today I'm going to present a part of the paper, The Complexity of Adversarially Robust Proper Learning of Half-Spaces with Agnostic Noise. This is a list of contents that we'll be going over today. First, I shall talk about the motivation of this paper, and next, in the section of hierarchy of problems, we shall go over problems such as pack learning, agnostic pack learning, half spaces, proper learning, and then we shall go to the problem that is stated in the paper. And finally, we shall look at the contributions of this paper. So the main motivation of this paper is the requirement to design reliable machine learning systems for secure critical applications. The main concrete goal is to develop classifiers that are robust to adversarial examples. And next, the challenge of this goal is to design computationally efficient classifiers that are provably robust to adversarial perturbations. Next, let us go over the notation and terminology that is used in the paper. C represents the concept class of Boolean valued function. X represents our instance space, which is a subset of the d-dimensional real space. H represents our hypothesis space on instance space X. D is the distribution on instance space X. U is the function defined on instance space X that gives all the possible perturbations given a sample from instance space X. And LP perturbations with gamma margin. This represents the set of all perturbations whose distance from X is less than gamma when measured using LP metric. And we shall consider the values of P which are greater than or equal to 2. Next comes robust risk. So the robust risk of a hypothesis H in instance space, in hypothesis space H with respect to distribution D on X with labels plus or minus 1 is defined as the probability that there is a Z belonging to the set of all perturbations of X, that is U of X, such that H of Z is not equal to Y, where X, Y are drawn from distribution D. Next, we shall briefly go over pack learning, that is probably approximately correct learning. Here, D represents the distribution on instance space X such that there exists a H star belonging to the hypothesis space H that correctly classifies all points. In general, this may be unknown to the learner. Next, we have epsilon, a constant such that it lies between 0 and 1 by 2. And next, we shall define the true error of a hypothesis as the probability that it will misclassify single randomly drawn instance from distribution D. And one important thing to note here is that this condition where we say that there exists a H star belonging to the hypothesis space that correctly classifies all points is known as the realizability assumption. Next, we shall formally define pack learning. So, consider a concept class Z defined over instance space X of length n and a learner L using hypothesis space H. C is PAC learnable by L using H if for all C belonging to the concept class, distributions D over X and epsilon such that it lies between 0 and 1 by 2 and delta such that it lies between 0 and 1 by 2. Learner L with probability at least 1 by delta output a hypothesis from the hypothesis space such that this error is at most epsilon. And it does that in time that is polynomial in 1 by epsilon, 1 by delta, n and size c. In layman terms, we output a hypothesis H with very high probability such that The error of this hypothesis is at most epsilon. So I would like to stress on this point that we are only given samples such that x1, y1, x2, y2 up to xn, yn from our instance space X drawn from distribution D, and this distribution is not known to the learner. Next, we talk about agnostic pack learning. So same as before, we have D as a distribution on instance space X and it may be unknown to the learner, and epsilon a constant such that it is greater than 0. The difference between pack and agnostic pack is that in the agnostic pack learning model, we do not have the realizability assumption. Hence, we cannot hope to output a hypothesis with error at most epsilon because the hypothesis might not even exist. So we compare it against the optimal classification error denoted by OPT, where OPT is defined as the infimum of all the errors, where the infimum is taken over all the possible concepts belonging to the concept class C. So the goal of agnostic pack is to output a hypothesis such that with high probability we have the error of this hypothesis is less than or equal to the error of the best fitting hypothesis plus epsilon. This work focuses on half spaces. So let us look at them. Given an instance space X, a subset of the D-dimensional real space, a half space HW is defined as the sign of the inner product of X and W. So if the inner product of X and W is greater than or equal to 0, it's labeled as +1 and -1 otherwise. And the class of half spaces is simply the class of all such half spaces W in R to the D. Next, we shall introduce proper learning algorithms. So an algorithm is called proper if it outputs a hypothesis H such that H belongs to the concept class C. Now we talk about the problem of proper agnostic pack learning of half spaces. So the goal of proper agnostic pack learning of half spaces is to output a half space hypothesis HW such that with high probability the error of this hypothesis is less than or equal to the error of the best half space hypothesis plus epsilon. So now that we have everything from the title of the paper, we shall define the problem of the paper formally. Given IID samples from an arbitrary distribution D on instance space X with labels ±1, the goal of the learner is to output a hypothesis H belonging to the hypothesis space such that with high probability it holds that the robust risk of hypothesis H is less than or equal to the robust risk of the best fitting function in C plus some epsilon. From hardness results, it follows that this problem is hard and we would need to relax this definition in some ways. So what we do is firstly we allow our hypothesis to be robust in a slightly smaller perturbation region. That is, we reduce the gamma margin to 1 minus nu gamma margin. I haven't noted this down in my slides, but nu is some constant between 0 and 1. And we also introduce a small constant factor approximation in error guarantee, and we denote this as alpha. So our goal is to now find a computationally efficient algorithm such that the robust risk of this set of perturbations with 1 minus nu gamma margin is less than or equal to alpha times the robust risk of the best fitting function plus epsilon. We also define another constant delta such that alpha equals 1 plus delta, where delta lies between 0 and 1, just as nu. So now that we have relaxed our definition, the authors say that this problem of adversarially robust agnostic pack model is equivalent to agnostic proper pack learning of half spaces with LP margin. Also, it should be noted that our functions are bounded by a d-dimensional LP unit ball BDP. So let us define this problem formally. Given IID samples from a distribution D over a unit ball BDP, which with labels plus or minus 1, for W belonging to BDQ, its gamma margin error is defined as the error of W is nothing but the probability of the sign of the inner product of W and X minus Y gamma being not equal to Y, where X and Y are drawn from D. And we also define OPT to be the error of the best fitting W from BDQ. An algorithm is proper new robust alpha agnostic learner for LP gamma margin half space with probability at least 1 minus tau if it outputs a half space W belonging to BDQ with error of W less than or equal to the alpha times the error of the best fitting function plus epsilon. Here we have introduced Q. Q is nothing but the dual norm of P. I'm sorry. Okay. Yeah, so here we are. What's happening? So yeah, so now that we have kind of translated or redefined the problem, I shall before defining the contributions of the authors through this paper, she'll go over this quick fact, like this is just something what we've defined before. So from agnostic proper pack learning of half spaces with LP margin, we're just showing that the robust risk of gamma margin is equal to is the same as the gamma margin error. So the gamma robust error is the same as the gamma margin error. And coming to the contributions of the paper, the authors have contributed two algorithms. So the first being the robust and agnostic proper learning algorithm for LP gamma half space with near optimal running time, and the second being a tight running time lower bound for robust L infinity gamma margin proper learning of half spaces. So coming to define the robust learning algorithm, the theorem is as follows. First, we fix P with this condition and gamma which lies between 0 and 1. For any nu and gamma lying between 0 and 1, this is a proper new robust 1 plus delta agnostic learner for LP gamma margin half space that draws big O of p by epsilon squared nu square gamma square samples and runs in time 1 by delta to the power of big O of p by nu square gamma square times polynomial in d by epsilon time. Furthermore, for p equal to infinity, there is a proper new robust 1 plus delta agnostic learner for L infinity gamma margin half space that draws big O of log d by epsilon squared nu square gamma square samples and runs in time d to the power of big O of d to the power of big O of log of 1 by delta by nu square gamma square times polynomial in 1 by epsilon. This seems like a lot, but here is like the summary of that algorithm. So considering the setting where delta equal to nu equal to 0.1, the time complexity when p is greater than or equal to 2 is this 2 to the power of big O of 1 by gamma square times polynomial in d by epsilon, and when p equal to infinity it is this d to the power of big O of 1 by gamma square times polynomial in 1 by epsilon. So for p equal to 2 and nu equal to 0.1, previous works have given a sophisticated algorithm with running time polynomial in d by epsilon times 2 to the power of big O of 1 by delta gamma square. The algorithm stated in this paper generalizes to all values of p. The next contribution is the tight running time lower bound, and the theorem is as follows. So the theorem says that there exists a nu greater than 0 such that, assuming the randomized gap exponential time hypothesis, there is no proper nu robust 1.5 agnostic learner for L infinity gamma margin half space that runs in time f of 1 by gamma times d to the power of small o of 1 by gamma square times polynomial in 1 by epsilon for any function f. The 1.5 in the above statement is insignificant and can be increased to any constant less than 2. If you observe 1.5 is nothing but the approximation factor alpha, and as we know alpha is nothing but 1 plus delta, and delta lies between 0 and 1, and hence we say that it can be increased to any constant which is less than 2. So from here on we shall look at some concepts that are required to prove the robust learning algorithm. So the first is the notion of online learning with margin gap, which is defined as follows. An online learner A for the class of half spaces is called an LP online learner with mistake bound M and gamma gamma dash margin gap if it satisfies the following. In each round, A returns a vector W belonging to BDQ. Moreover, for any sequence of labeled examples xi, yi such that there exists a W star belonging to BDQ with sign of the inner product of W star and xi minus yi gamma equal to y, for all I, there are at most m values of t such that the sign of the inner product of wt xt minus yt gamma prime not equal to yt, where wt equals a of x1 y1 x2 y2 and up to and all the samples up to xt minus 1 and yt minus 1. So this seems like a lot, but when simplified it is as follows. So for a given round t, a learner has a half space wt. Then the learner is given xt from BDP, and the learner tries to predict this label using the current half space WD. After he has made the prediction, the true label YT is given to the learner. And using this true label, the learner updates half space to WT plus 1. And coming to in this definition, we have introduced something called as gamma gamma dash margin gap. So gamma margin assumption states that there exists a half space W star that correctly classifies all the samples. And coming to gamma prime margin error, a learner is said to make a gamma prime margin error in round T if the learner doesn't classify the sample XTYT correctly with the margin gamma prime. Also, here the number of rounds is at most m, where m is the number of mistakes that our learner can make. And now that we have introduced gamma prime margin error, so the gamma prime learner means that the learner makes gamma prime margin mistakes under the gamma margin assumption. And would also like to make note of the contributions by Claudio Gentil, who gave a polynomial time LP online learner with margin gap gamma 1 minus nu gamma with mistake bound of big O of p minus 1 by mu square gamma square for values of p lying between 2 and infinity, and a mistake bound of big O of log d by nu square gamma square for p equal to infinity in his paper, a new approximate maximal margin classification algorithm. So here is the proposition. So the proposition states that assuming that there is a polynomial time LP online learner A for half spaces with a gamma gamma dash margin gap and mistake bound of m, there exists an algorithm that given a multiset of labels labeled examples S, which is a subset of BDQ with labels plus or minus 1 and delta belonging to the open interval 0, 1, runs in polynomial of cardinality of S times D times 2 to the power of big O of m log of 1 by delta time, and with probability 9 by 10 returns W belonging to BDQ such that the error of this W is less than or equal to alpha times the best fitting W, where error of W is given as follows, which is practically the same as before. Also, here is something that I didn't mention, but will add to my slides later on, is that instead of D, S is used to denote the empirical error on the uniform distribution over S. So we now modify this proposition to the following lemma, which has a small success probability, but it is faster. So what we do is that we run this lemma many number of times and return the best W. So the lemma is as follows. Assuming that there is a polynomial time LP online learner A for the half spaces with a gamma gamma dash margin gap and mistake bound M, there exists an algorithm that given a multiset of labeled examples as a subset of BDP and delta belonging to 0, 1 runs in polynomial of cardinality of S times D and with probability 2 to the power of minus big O of n log of 1 by delta, n runs W belonging to BDQ such that this error is less than or equal to 1 plus delta time the error of the best fitting W. Also, I think I've made a mistake here. S belongs to BPD and not BDP and not BDQ. So the lemma here says that given an online learner A with a gamma gamma dash margin gap and mistake bound M, in a given round it randomly picks a sample that is not correctly classified by WT with a gamma dash margin gap, and we allow A to classify this sample to get a new half space WT plus 1. The best half space is delivered as the output. So I end my presentation here. In the next set of slides, I shall talk about Theorem 2 and additional concepts that are required to prove theorem. In the next set of slides, I shall talk about the proof for the robust learning algorithm and discuss concepts that are required to prove our theorem 2, that is hardness result. Thank you.